everyone. Welcome and thank you for joining us for this webinar titled Using Benchmarking to Design 5G Telco Clouds, Optimize Virtualized Infrastructure Using Repeatable Performance Testing. My name is Liz Garcia and I am your moderator for today's event. Your panelists for today are Bill Queen and Vlad Laszlo. You will first hear from Bill Queen, Director of Business Development at Keysight. Bill is focused on cloud computing, NFV, and active monitoring. He has extensive experience in enterprise computing and networking and is responsible for developing new business and products for the Ixia Solutions Group at Keysight. Then you will hear from Vlad Laszlo, Senior Technical Product Manager responsible for virtualized test solutions at Keysight. In this role, Vlad manages multiple software products which are used to validate virtual networks. And here is our agenda. I'd like to highlight that we will take questions at the end of the presentation. Please submit your questions at any time using the Q&A chat window. Your questions will not be seen by any other audience members. Only the presenters and I can see those on the back end. So please submit your questions at any time and we will answer those at the end of the presentation. And as you can see, we are covering a lot of material. So I will now pass the virtual mic to your first presenter, Bill Queen. Bill, take it away.
Thanks, Liz, and good to be here today with all of you. First, let me take a second just to introduce Keysight for those who aren't familiar. Keysight's the leader in 5G network test and measurement. We have an extensive set of capabilities from RAN to core and from layer 1 to 7, especially after our acquisition of Ixia a few years ago. And we're also technology leaders in a number of other areas, including automotive, aerospace, electronic design, and IoT. So now let's dive in and talk about the challenge of high-performing NFV and cloud-native telecom networks. The backdrop here is that NFV and now cloud native really forces telcos to take on the role of system development. And this is a big reason why NFV so far has disappointed. Before virtualization, you'd buy a complete product like a new car where someone else had thought through how it all works together. And then you connected things in standard ways, and there were some integration problems and some major problems around automation, but it was a pretty static environment and things worked okay. But now with virtualization, and here I'm referring to cloud native as well, we get a box of parts and it's up to us to put it all together. And since the goal is cloud native, we have to do this in a way that's dynamic and flexible. We need the network functions to be able to run on any infrastructure. We need to be able to mix different types of network functions and to set policies so that we can utilize all the capacity of that infrastructure. And this is really hard. The alternative is that we end up with something that's called NFV, but it's really just another version of an appliance. So if we look at all the stages of virtualization, and here I have a block diagram of virtualized servers on the bottom and the NFV Nano system on the right. In terms of the stages of virtualization, first we have what's in essence a virtualized appliance. This is simply a VNF running on a hypervisor. It's not very different from hardware. And then we have basic NFV, which is scaling multiple VNFs, but of the same type, for example, a P-gateway VNF. And this is a marginal improvement over the virtualized appliance. And then we have what I'll loosely call advanced NFV. And this is when we start adding other types of VNFs that are all coexisting and performing well, and at relatively high levels of infrastructure utilization. And this is getting to be really hard, and I don't think anyone has really nailed this yet. And so we have to make lots of choices here as we're building the system. For example, about the NIC, different vendors, speeds, SRIOV and DPDK, and so on. About the CPU, about storage. and about memory type and virtualization, and the Vim, for example, OpenStack or VMware or something else, one of the many proprietary orchestrators, and which vendors do we choose for the other technologies, and then there are upgrades. Even a simple upgrade to a newer CPU can have unexpected consequences. And then on top of that, we have cloud native, and that means another level of flexibility in the system. And basic decisions like whether to run containers and VMs to take advantage of the extensive management capabilities of VM infrastructure, or to run on bare metal become important. And so there's a tremendous amount of complexity here that's very difficult to deal with from a design perspective to really deliver on the promise of cloud native. So I want to take a second here and review a sampling of real problems that our customers have faced. And one, obviously, is the vendor and technology selection that I mentioned before. The CSP that I'm thinking of here was running performance tests using actual VNFs to make these choices, and this was an extremely time-consuming and also not very reliable or repeatable process. And it really couldn't deliver the insight that they needed to make these decisions. A second example is another one of our CSP customers who's trying to size universal CPE, with the first problem being to determine the capacity of the NFVI for a pool of DNF types like firewalls and SD-WAN and so on. And then they had the additional challenge of allocating capacity to the customer to run applications and provide specs for that. And it's a very complex set of scenarios that really requires a rigorous methodology in order to be able to properly spec out and ensure that the whole system is robust and performant. And third example here, one of our CSP customers began experiencing performance problems with VNFs after an OpenStack upgrade. And they'd done the normal validation in the lab. And this was extremely hard to troubleshoot. And ultimately, it was due to a configuration problem that affected only certain nodes. But the validation was limited to a small-scale implementation, and so this became a very non-obvious issue and very difficult to debug. And so with these issues, 5G makes it even harder. We need to design this high-performing cloud-native system that can scale quickly, both in capacity and in service types on a flexible pool of architecture. It's got to be cloud-native. This means cloud-native containerized CNS, where profiling becomes much more of a moving target, since the VNF is now decomposed into independently scalable services. The profile can change significantly, and it's much more dynamic. The CNFs themselves are ephemeral, so the scaling can be quite rapid, and the resource profile can change quickly. And then we have edge computing, and this is going to further complicate everything. Everything becomes much more distributed. In a 5G system, the UPS will move much closer to the edge, where it'll be much more expensive to over-provision and silo NFV capacity. And so we're trying to design this really high-performance, complex superhighway system. But without a good methodology, we end up with something that looks more like this, a hopeless helter-skelter traffic jam. So how do we solve this? Well, first, you can profile the actual applications and do exhaustive integration and scenario testing. This means taking the actual application and really putting it through its paces on the infrastructure. And as we've discussed, this is extremely time intensive. It's not repeatable and scalable. And in the end, it's also not very exhaustive. It's very hard to hit all of the different cases that you need to hit. So what we need is a repeatable, automatable, and scalable methodology to do this benchmarking. And so now I'll pass it to Vlad to talk about methodology for benchmarking.
Thanks a lot, Bill, and hello, everyone. Indeed, the challenge that you have described looks very complicated. There are so many moving pieces. So as you mentioned, we need a benchmark methodology for this. Let's dive a little bit into the options for such a methodology. So discussing about marking virtual infrastructures, we have been having such discussions with many customers. And many of them have been telling us that, hey, benchmarking is a little bit complicated for me. Is there an easier solution? Is there a faster way for me to get the answers that I need? And such a solution might be, some of them think, to simply look at the data sheets from the vendors, to analyze the virtual infrastructure data sheets, to analyze the specifications from the vendors, and based on those specifications, to draw conclusions and to make sure that the infrastructure indeed behaves according to what the vendor says. But you cannot always trust the vendor. This is one aspect of it. And the second and more important aspect is the moving pieces, is the complexity of many elements that need to be integrated together. And there is no data sheet to say how a specific infrastructure will behave with a VNF from a different vendor. Therefore, relying simply on the data sheets is not sufficient. The other choice of benchmarking virtual infrastructures is, as Bill mentioned, to use real applications, real VNFs, and benchmark. But do you really afford to spend the time, to spend the resources, to do the benchmarking across multiple clouds? Do you trust that the results are repeatable and reliable, so every time you have a problem, to use this application type of benchmarking and rerun the same application and make sure that the results you are getting are relevant for the problem that you encountered? So these are basically two extreme scenarios for benchmarking virtual infrastructures. What we propose is kind of a middle ground to use a tool for benchmarking the infrastructure, and that tool should supply a set of key performance indicators that are relevant for the infrastructure, but are also useful for the applications or the VNFs running on top of that infrastructure to predict how a VNF would behave. So let's dive in a little bit. So let's look in more details how to benchmark virtual infrastructures. What do we need from a virtual infrastructure benchmarking methodology? We need several characteristics. We need the benchmarking methodology to provide relevant statistics which are useful for the applications running on top of that infrastructure. We need obviously reliable measurements which can be trusted, and we need repeatable results which measure the same KPIs, the same statistics under the same conditions and provide the same set of results. Now, looking a little bit closer, first of all, we need a benchmark methodology which isolates the virtual infrastructure performance across different categories. And when we say categories, we are referring to compute, network, storage, and maybe virtual infrastructure manager performance. Afterwards, we need to understand the key performance indicators within each resource category. As an example, in the compute category, you might want to look at the CPU cache memory performance, or at the memory latency, or at the memory bandwidth. Similarly, we have KPIs for storage, such as read and write operations, bandwidth, IOPS, and latency. And network, we have a ton of KPIs such as throughput, loss, latency, jitter, and so on and so forth. After we have identified the KPIs, you need to characterize the application behavior and understand what kind of resources it uses. Is it a CPU intensive, is it a network intensive, or maybe is it a storage intensive application that you are planning to run on the virtual infrastructure? Next, after you have understood the application, you need to model the application into test scenarios. Design some test scenarios which benchmark the resources that the application will use. After we have modeled the application, we will then execute the benchmarks and collect the relevant statistics. And once we have the statistics, we will analyze the results from the benchmark. We will compare the systems or compare the before-after scenarios and choose the best action. Maybe choose the best vendor or choose the best configuration. With this being said, this is the theory that we have discussed regarding benchmarking. But let us now look at several benchmarking examples, real-world examples, how we can use benchmarking in order to to answer some of the pressing questions. First of all, analyze a little bit the system under test that we are using for these results. So we have two systems under test, but they are sharing a common hardware platform. You can see here the hardware specifications. It's not the latest and greatest hardware, but also it's not a very old platform, so it's something that is very common across many of our customers. And what is different between these two platforms? The software, the Virtual Infrastructure Manager. One of them uses VMware vCenter with ESXi hypervisors and VDS for switching, and the other one uses OpenStack Queens with KVM hypervisors and OVS for switching. These two systems will be used in the following examples. So let us start with example number one. Let us start with scenario number one. And in this case, let's say we have a telco with an existing NFV environment, and the existing NFVI is planned to be decommissioned and planned to be replaced with a newer hardware generation. And the hardware has already been selected, but now you have a choice between different virtual infrastructure managers. How to choose which VM is best, depending on the applications you are planning to run on that NFVI. And which are the applications? The most resource-intensive application at the moment is a VNF, it's a vRouter, which has BGP responsibilities, a BGP route reflector, which stores the entire internet routing table. So with this being said, you can see how the VNF is very memory intensive. We need to select a hypervisor, which is very good at providing top memory performance. How do we do that? Not like this, just wondering. We need a clear methodology. And for methodology, we want to benchmark 3 elements. First of all, we want to benchmark the memory latency and look at the average and maximum latency across level 1, level 2, level 3 cache memory from the CPU and system memory. Then look at the memory bandwidth between the CPU and the system memory. And lastly, look at the memory stability for long-duration system behavior. Let's look at some benchmarking results. Starting with memory latency, and in the upper right section here, I have some parameters for my benchmarking test. So I have the memory size, which is 1 gig. I have the stripe, basically, which is the amount of bytes that I'm starting to read and write from that 1 gig. And more importantly is the SLA, or the expected result. The current system has a latency of 30 nanoseconds, a maximum latency. Let's look at the new systems. What results do we get from those new systems? So if we look at the benchmark results for system number 1 and system number 2, you can see they are very similar. They both pass the test, meaning they both provide better results than the system to be replaced. To analyze this a little bit more closely, you can see that when reading and writing in the level 1 cache, the latency is very, very low, slightly higher for level 2 and then again higher for level 3, but it's a big jump in latency when going through the system memory. And you might say that the systems are identical from this perspective, but looking even more closely, you can see this is not the case. You can see that the maximum latency for system number 1 is around 23 nanoseconds, and for system number 2, it's around 27 nanoseconds. So that's one aspect, and the second aspect is the average latency, which is about 1 nanosecond difference, 985 versus 1142. So with these two differences, although both systems are better than the one to be replaced, you can already see that system number 1 is slightly better. Next step, we leave the latency comparison behind and we look at the bandwidth. And for bandwidth, we do read and write operations with 10 meg memory pages, and we repeat the same measurement 2,000 times. This is a very repetitive operation. And the result for the existing system is 18 gigabytes per second. Let's look at the results. You can already see some pretty large differences. So for system number 1, you can see that all the 2,000 iterations are passed. And basically in here, the green line is referring to the measurements, and the orange horizontal line is the SLA, or the threshold to be exceeded. You can see that system number 1 is much better than the one to be replaced. while system number 2 has results all over the place. It actually has 61 failed iterations because there is a lot of variability in the results. Looking simply at the average values doesn't take the entire picture. So on average, system number 1 has 19.7 gigabytes per second. System number 2 has 18.85 gigabytes per second. So there is a difference, but not a huge difference. However, when you look at the variation of 1.5% versus 14%, we can see that system number 2 is much less predictable, much less stable, much less reliable than system number 1. So with this being said, I think at this point we can simply exclude system number 2 and say that this is not good enough for us. It's not better than the one to be replaced. And the last step, we have already selected system number 1, but let's look a little bit at the over long duration. So in order to do that, we have exactly the same benchmark, but now we are repeating the measurements 10,000 times instead of doing the measurements 2,000. Looking at the results, in the upper section we have the same results from the previous slide, but in the lower section you can see that once we have the test running for a much longer duration, we start to have some failures. So out of 10,000, we have 18 failures, and those failures only happen after a while, after about 3,000 iterations. So the first result, which 2,000 iterations passed, that still stands. So in this case, we have more or less the same average, but the variation is much higher in long duration. So this result, I think it's worth to be further investigated. So this is something that would leave in my mind a question mark on this system number 1.
Vlad, I just wanted to add to that. I just wanted to interject real quickly that this kind of information is really useful, not just when you're trying to to compare and select technology and vendors, but it's also extremely useful when you're trying to understand a sporadic issue. For example, in this case, where there might be a sensitivity to latency, right? So this can give you a lot of insight as you're trying to troubleshoot actual issues.
That's a very good point, Bill, and I really appreciate your comment on this slide. And indeed, this particular result might seem odd at the beginning, but this is something that needs to be investigated, either directly by the telco, either together with the vendor that designed the infrastructure. And just to conclude on this scenario number 1, review for a second what we did so far. So we have an existing infrastructure, and we have a VNF which is memory intensive. That existing infrastructure has 30 nanoseconds of latency and 18 gigabytes per second of bandwidth from a memory perspective. But that infrastructure is planned to be decommissioned. And we have two choices, same hardware but different software. SUT number 1 versus SUT number 2, you can see that both pass the latency test, but the first system is significantly better than the second system. Still, this doesn't exclude the second system yet. It just puts a question mark on its ability. The second set of benchmarks refer to the memory bandwidth. And in here, although from an average perspective, they both exceed the expectations, from a variability perspective, system number 2 has been very poor. So it has 14% variability in the results. The test failed, and it is at this point where we can already exclude system number 2. And the last step that we did was to validate the stability of the memory over long duration, and there were some failures in here. So this is something to be further investigated. The conclusion from my perspective is that it's easy to choose system number 1, but then system number 1 is not perfect. There are still things to be tuned and maybe investigated together with the vendor. And Bill, let us know if you have other observations on this one.
Yeah, actually, I just wanted to interject that this can be important in a number of ways. So for example, if you're trying to evaluate different software stacks, different VIMs, for example, this can be this kind of testing is extremely important to do, because you'll find that the behavior can be quite different across these, and our customers have seen this in a very strong way. So thanks, Vlad.
Thanks a lot. So with that being said, let us move forward to a sample, and let's look at another VNF and analyze how we can benchmark the infrastructure from the perspective of that VNF. So for scenario number 2, we have a VNF which has the role of doing traffic analysis, and it's collecting a lot of metadata, and it's logging that metadata to storage. So it's a VNF which is very storage intensive. It's not reading and writing huge chunks of data to the storage. It's reading and writing, and especially writing small chunks of data, but it does so very often. So that's one aspect of the scenario, how to benchmark the storage to make sure it's good enough for this VNF. But then we have a second dimension. This carrier also wants to implement at a later stage network slicing. And for that, he will provide multiple slices to different customers, but he needs to do traffic analysis within each of the slices. And for data governance reasons, he needs separate VNFs to process traffic from the different slices. So depending on how many network slices there will be, multiple such VNFs will be hosted on the same infrastructure. We need to understand how many storage-intensive VNFs can be hosted simultaneously on the same NFVI without having severe performance degradation. What is the answer? Again, this is not a good answer, this is not a good approach, but methodology is the answer to these questions. We need to benchmark the storage stability. We need especially to focus on storage scaling, and in my case, I have selected 2 cases with 10 VNFs and 20 VNFs. And for these cases, we want to look at write operations and measure the bandwidth, IOPS, and latency in both of the scenarios. Let's move ahead and look at the results. In the upper right section, I have the parameters of my test. This first test has a single copy of the VNF. So you can see VNF count is 1, and it's writing a block size of 4 kilobytes. From an SLA perspective, from a threshold, from a pass-fail threshold perspective, we have the bandwidth, IOPS, and latency. And the initial values are the ones that were suggested by the NFVI vendor. The NFVI vendor said that the platforms should be able to do 600 kilobytes per second, 150 IOPS, and 7,500 microseconds maximum latency. So these numbers are not very high. This signals that this is a hard drive-based platform and not an SSD-based one, and it was designed like this because of the huge amount of storage needed over the long term. Let's look at the results. So first of all, from a storage scaling perspective with a single VNF, the test has passed for a long duration. We have in here the write bandwidth, the write IOPS, and the write latency. And for the bandwidth, we can see that the average is around 681 kilobytes, while the minimum is 605 kilobytes. So the minimum is just above the SLA. Similar for the IOPS, the minimum IOPS is 151, and the maximum latency is slightly less than 6 milliseconds. So looking at these results, what we can see? We can see that the test is passed, and we have several observations. First of all, we have KPI variation. You can see this sign pattern because of the spinning disks. Depending on where on the disk the data is written, closer to the edge or closer to the core of the disk, also the storage performance varies. So this tells us that we need to take into account this variability which cannot be controlled and plan for this variability when designing the overall system. But even with this variability, the minimum and average values are still better than the SLA. So the test is passed. But what a negative spike in all the charts, and it looks like a noisy neighbor. What happened in there? Can we further investigate that scenario? So yes, we can investigate it, and we can actually zoom into the data, and we can see the exact timestamp when we had an event happening. With this timestamp, we can then investigate what happened in the system. Basically, in my case, while the benchmarking was running, I started another virtual machine on the same server, and that virtual machine, while it was booting, it was reading and writing on the disk, basically affecting the performance of my benchmark. So this tells me that although the performance is good, it's not isolated from somebody else. Anybody can run on the same platform and anybody can act as a noisy neighbor. So this is something a little bit of concerning. You might want to think of isolation between VNFs, or you might want to think of different ways to negate this behavior of a noisy neighbor. So this is storage scaling with a single VNF. Let's go into details. Let's see what happens when you have 10 such VNFs writing simultaneously to the storage. If you look in the upper right section, the storage VNF count has increased with a 10-fold factor, and also the SLAs, we have decreased the SLAs by a factor of 10, because the same resources are now shared between 10 VNFs. So our expectation is only 60 kilobytes per second, only 15 IOPS. Looking at the results, we can see that out of the 10 instances, 9 have passed and 1 failed. And let's look at the charts to analyze exactly what happened. We can see now the charts are slightly different. They are clusters which represent all sorts of data results across the time scale and across the performance scale. So basically aggregating data from multiple instances, we display them on a charter, on a cluster, in order to understand what is the most common value that is seen in the benchmarks. And looking at the orange line over here, we can see most, if not almost all the cluster results are above the SLA. Only a very single result is below the SLA for bandwidth and IOPS, and there are no results above the SLA for latency. So with that being said, we can say that the test is almost passed, almost, because you have some KPI scattering because of random access. You have most of the KPIs values better than the SLA. Actually, the worst case scenario is 59 kilobytes per second and 14.79 IOPS, which is ever so slightly below our expectation. So we can be indulgent here and say, yeah, the test has passed. So with 10 VNFs, the system behaves all right. Let's move to and let's see what happens in this case. With 20 VNFs, only 2 of them have passed and 18 have failed. Looking at the clusters, you can see that there are a ton of results below the SLA for all the charts, bandwidth, IOPS, and latency. And you can see that the minimum bandwidth is now 12 kilobytes per second, and the minimum IOPS is 3 IOPS. So we basically doubled the load, but the performance was impacted by a factor of 4 or even a factor of 5. So this tells me that the system has exceeded the limit. It's no longer capable of sustaining the load of 20 simultaneous VNFs. With this conclusion, we can basically exclude the 20 VNF case because it has clearly failed and the results are worse than the SLA, and the NFVI is clearly oversubscribed and cannot sustain 20 VNFs, which basically refer to 20 network slices in parallel. Reviewing this once again, let's see what we have done in this example. So we have a system under test with a storage intensive VNF, and these are the KPIs to be tested, the claims from the NFVI vendor. The first test, we run it with a single VNF, and we run it for a long duration to test the stability and the minimum bandwidth IOPS and the maximum latency. They are both better than the expectation. So the test in this case is passed. But also, as a side discussion, we have seen what effect a noisy neighbor can have. So a noisy neighbor can have a negative impact, and this needs to be further investigated, how we can avoid such cases in a production network. The next step was to increase the VNF count from 1 to 10, but also decrease the SLAs by a factor of 10. So in this case, the test is passed, but only just. Its minimum bandwidth is 59 kilobytes per second, just slightly below the 60 kilobytes, similarly for IOPS. So I wouldn't call it failed, I'll just put here a question mark. And the last result was the one with 20 VNFs, and you can see how doubling the load has led to much poorer performance. Actually, if you look at the latency, it's 300 milliseconds. For a storage, 300 milliseconds is huge. This already starts to generate application failures. So we can clearly eliminate this case and say that the system is not capable of sustaining that many VNFs. With that being said, let's move on of the presentation, and let's discuss how we actually implement this benchmarking process into a product. And let us introduce the product, which was used to collect all those benchmarks. The product is CloudPeak, and it is a tool for performance and capacity benchmarking across the cloud infrastructure. And it refers to any type of cloud. We have focused on telco clouds, but the same benchmarking methodologies can be used for public, private, or hybrid clouds. And what does the product do? The product models virtual machines and generates synthetic behaviors, synthetic workloads to deliver KPIs in order to characterize the cloud infrastructures, identify configuration issues, and see where is the performance bottleneck of that infrastructure. This product compares infrastructures from different vendors, optimize configurations across those infrastructures, and identify bottlenecks. And it does so across compute, network, storage, and also the software layer. So comparing the infrastructures might be done, for example, for vendor selection, choosing the hardware or choosing the software as we have seen in our examples. Optimizing the configurations might referring to optimizing, let's say, the network drivers, or optimizing a particular compute node in the configuration files, or optimizing after an upgrade process if something didn't work well after the upgrade. And lastly, identifying bottlenecks in here refers to either determining the peak capacity of a system, like we have seen in the second example, or to identify bottlenecks when you have something performing poorly, to identify what is causing that behavior. And let's discuss a little bit benchmarking telco clouds with CloudPeak. So the use cases that I'm going to present right now are the following. Performance comparison between different vendors. Select the vendor, either hardware or software. This is what we did in the first example. A second use case in here is, as previously mentioned, is to optimize infrastructure. And the third use case is to measure the peak capacity, to determine the peak workload utilization in order to understand how much can the infrastructure cope with. Basically, this helps you get very familiar with your NFVI. And let's discuss a little bit product works from an architecture perspective. So the product is basically a software tool, which is a set of virtual machines. You have a CloudPeak management instance, which the user can connect to either via the GUI, either via the API. This GUI basically comes with a set of predefined test methodologies. The user would pick one or multiple methodologies, would add them to a playlist for execution, would parameterize those methodologies, and then create individual test cases based on the application needs, and then will start the execution of those benchmarks. And when the execution is started, the product connects to the Infrastructure Manager API, be it OpenStack API or be it VMware API. It automatically deploys a set of test instances onto the system under test and then executes the benchmarks. It can also deploy in parallel noisy neighbors to emulate what happens when you have a high load on the system. Basically, the noisy neighbors are some VNFs which are very resource intensive and are trying to steal resources from the good VNFs. Let's call them bad guys and good guys, and the noisy neighbors are the bad guys in our case. And they can be, for example, a VNF which was poorly programmed, or they can be a VNF which has crashed and it's using the CPU at 100%. With all these virtual machines running either in parallel, either sequentially on the system under test, we will then connect to the system, to the virtual machines onto the system under test, execute the benchmarks, collect the statistics, and at the end, if needed, we can also destroy the environment and return it to the original state. So this is how the benchmark happens, and it has the advantage that inside these virtual machines we have some workload emulators, and we benchmark the resources which are exposed to the VNFs. So the metrics we collect are the same metrics that a VNF would see running on the same system under test. And this product, CloudPeak, is a solution for benchmarking the system under test, which is the NFVI infrastructure. This is part of a complete telco cloud solution portfolio. We can also use other products in our portfolio to benchmark a system under test, which is composed of different VNFs, different applications. And for example, you could use IX Network for benchmarking virtual routers, or IX Load Virtual Edition for benchmarking voice and video traffic, or benchmarking a 4G EPC type of scenario. And also you can use Breaking Point Virtual Edition to benchmark the security of the VNFs, for example, virtual firewalls. CloudPeak and the rest of the products from our portfolio are complementary, and they can be used independently or they can be used together for a complete end-to-end benchmarking of the VNF and of the infrastructure. And these products together can help you design a 5G telco cloud which can cope with the needs of your users. With this being said, I have a pre-recorded demo that we will play to actually show you the product UI and show you how to run several benchmarks. Let me start the demo. Let us start with the demo, and we'll do so by logging into CloudPeak and seeing that in CloudPeak we have multiple test sessions which are already opened. Some of them testing VMware or OpenStack system under test, other testing public cloud or telco clouds. For the purpose of this demo, I will start a new test session because I want to pick some tests from the repository of pre-installed tests and add them to a playlist. You can see here that the repository contains multiple methodologies: network, storage, compute, custom methodologies. And for this demo, I'll try to replicate the examples presented in the slides. And so I'll add a memory bandwidth, a memory latency, and a memory storage performance type of methodology. Each of these methodologies can be further parameterized and then turned into multiple individual test cases. For example, for a storage test, you might want to specify how many instances do you want to deploy: 1, 10, 20, maybe 100 instances. Then what type of operations: read or write operations, random, sequential, mixed operations. The block size, the number of iterations, the duration of each measurement, and so on and so forth. And another set of parameters you might want to configure are the SLAs. This is what determines whether the test has been passed or failed. These are configured based on your expectations. So with this being said, you would go ahead and parameterize every single test. Memory latency obviously has a different set of parameters similar with memory bandwidth. And then you start the test execution against the system under test you have identified, be it OpenStack, VMware, or be it somewhere else. For the purpose of this demo, I have already created a test configuration which I will load right now. And this test configuration has two playlists with a set of identical tests between two systems. SUT number 1 contains bandwidth, latency, and storage. And similarly for SUT number 2, and you can see that the parameters against the two systems are the same. Without further ado, I'll start the benchmarking. And what happens behind the scenes? CloudPeak connects to the system under test. It deploys the test instances, and then it starts the test execution according to the parameters identified in the test configuration. In here, we are benchmarking SUT number 1, and we are measuring the memory bandwidth, and we are expecting the test to pass if the measured bandwidth is higher than 18 gigabytes per second. The test is already running, and we can click on the script report to see the live dashboard with the actual results. And in the live dashboard, we can see that 23 iterations out of 100 have already finished and all of them are passed. And they are passed because the measurements, which are represented with a green line over here, are better than the SLA, which is the orange line. And if I refresh this page right now, you can see that already almost 60 iterations are finished. And you can see that the average result is around 19.6, 19.7, very close to the result presented earlier during the slides. So this is how a first test would run, and you can see how fast the execution happens against the system under test. But in order to continue the demo, I want to show you a test execution which has already previously finished. So I'll close this page and switch to a new tab where the execution is already finished. And what we see in here, for system under test number 1, we can see that all the tests have passed, while for system under test number 2, we can see some of them have failed. And if we compare, for example, a pass result for the memory bandwidth in here, we can see that the pass result has a horizontal line which is pretty stable and pretty in a small interval, so with very little variability. And you can see the statistics in the bottom right section. If we switch to the other test which is failed, and we look at the report for that other test, you can see how the results are more or less all over the place, and you can see that 6 iterations actually fell below the orange line, which is the threshold. So just shifting between these two tests, it's very easy to tell which one is better and which one is worse. And based on this execution, you can select which system is best for your needs. In our case, based on the applications that we are trying to emulate, system under test number 1 would be an obvious choice. Before concluding the demo, I want to also show you some results generic across the entire product. For this, I opened the generic dashboard, and in here I have compute, storage, network, and custom tests, some of which are passed, others are failed, and you can see the full list of results here in the bottom section. If I want, I could filter, for example, based on VMware, and you can see the failure and the pass rate across various categories for this particular system under test. This being said, I want to now conclude the demo and return to the slides to discuss how we can automate and to discuss the conclusions.
So now that we understand how benchmarking can be configured, executed, and analyzed with the right tools, let's talk about making the whole process agile and repeatable, which is crucial to making this a successful methodology. So in terms of automating the process itself has a few distinct steps. So first, we want to start with building test templates for key workloads in CloudPeak. And this is something that you only do once or when your workload requirements change. Second, the first step is to provision the workloads using CloudPeak. And this is something that can be scheduled or it can be on demand, maybe in a CI/CD pipeline, or something you do on demand to validate an architectural change or troubleshoot an issue. And the test could be run on a server or on a large number of servers, some part of a production cloud. And then you want to load the templates and execute the tests. And now we can review the results and quickly identify and drill down into the failures, anything that failed to pass the SLAs we defined. And last, the cycle needs to be repeated. So for example, to check stability of a production cloud, or we talked about some of the on-demand use cases. And the good news is that all of this is automatable via CloudPeak and the CloudPeak API. So all you need to do is to run a shell script or whatever your preferred framework is to execute the sequence. And so this gives you a very powerful methodology to benchmark, evaluate, and validate infrastructure and design choices, as well as a methodology to track drift over time, to detect performance issues that are inevitably going to arise. And so now Vlad and I would like to briefly recap what we've discussed here. NFV and cloud native computing for telecom is really hard. It's arguably much harder than for standard cloud workloads. So it's really difficult to make technology choices and vendor choices, and even simple things like upgrading CPUs or software versions can cause unexpected changes in performance.
Yeah, and to add on top of that, Bill, you need to measure the telco cloud performance. But how do you do that? Do you use actual DNF for benchmarking? That is too time-consuming, too complicated, not enough predictable, if you will. And another option would be to use the vendor datasheet for the infrastructure and for the VNFs. But in our opinion, these two options are not good enough. So a third option to use benchmarking to take informed decision is what we propose here. And benchmarking, you need to think of a benchmarking methodology, and that methodology was explained during the presentation that needs to take into account also the VNF characteristics, and also of a tool to implement that benchmarking process.
Yeah, and last, you need to implement an automated and efficient and repeatable methodology. And you really need a methodology to continually benchmark in a way that you can map to actual application performance. And so now let's go to questions.
Thank you so much, Bill and Vlad, for walking us through all that information. Now it's time for the question and answer session. A reminder to the audience to please submit any questions that you have in that Q&A chat window. I'll give Vlad and Bill a moment to look through those before I start asking any questions. If we don't get to your question during this presentation, we will follow up with an answer via email. So please feel free to submit those questions still. And before you exit this event, we would appreciate it if you take the survey. Your feedback is appreciated, and we'll use it to improve events going forward. I also wanted to take a moment to highlight additional resources. We have a CloudPeak data sheet available, as well as a demo. So you could visit the link on your screen, or you could visit the resources tab, and we have direct links to these assets within your console. And without further delay, I'm going to jump into the question and answer session. And now for our first question. Who would like to take this one? I have some network issues in my telco cloud. What kind of network benchmarks are available?
I can take this question, Liz. So indeed, this is a very good question, because during the webinar, we haven't discussed much about networking. We have focused on compute, specifically on memory benchmarking and on storage benchmarking. But obviously, we can benchmark network resources. And what we observe is that network is an area with multiple problems. And that's why, from a product perspective, we focused on multiple KPIs in the network. We have KPIs such as frame loss, frame rate in terms of packet per second, bit rate, for example, latency and jitters. So pretty much everything related to networking. And also for networking, standard networking uses virtual switches. But in telco environment, SRILV is very popular. And we also support SRILV interfaces from 10 gig all the way up to 100 gig. And one last thing for networking, especially for higher speed, DPDK acceleration is important. And DPDK is supported, and we can do up to 100 gig throughput at 1500 bytes frame sizes. So I would say that networking, pretty much everything is covered. All the metrics, all the scenarios, we have very good coverage for testing the networking of the telco cloud.
Perfect. Thank you, Vlad. This next question sounds like it's for Bill. What is the difference between noisy neighbors and test instances?
Thanks, Liz. That's a great question. So test VMs or test containers are designed to measure the amount of available resources. So with nothing else running, this would tell you the full capacity of the system, or with other workloads running, it'll tell you the available capacity. So Noisy neighbors are very different. They're a special type of test function that's used to add a specific load in the background. So, for example, you could set up a noisy neighbor instance or container to consume half of the CPU cycles. And the usefulness here is that you can control and constrain the load that it applies, and then you can look at how the available capacity varies depending on that. So what you'll find is that if you have a noisy neighbor that's consuming half of the CPU, you don't actually have half of the total CPU cycles available. It's less than that due to overhead and conflicts. And so these two types of instances or containers complement each other in the testing methodology.
Next question. The examples and the demo are based on VMs. Can you run the same benchmarks in containers?
Very good question. I can take that question, Liz. So indeed, once again, as in my previous question, we have focused on virtual machines during this webinar. But yes, we can benchmark Docker containers. And actually, we have seen that these are becoming more and more popular, especially with the proliferation of edge clouds or micro clouds. Running Kubernetes, running containers in such clouds, still in the telco environment, has become very popular. And even this week, if some of you have already attended the Open Infrastructure Summit and have attended some of the Kubernetes or container sessions, you have seen how much the industry is focusing on that area. So from our product perspective, yes, we do have integration with the Kubernetes API, and the same workloads that you have seen, the same type of benchmarks, can be run in benchmark containers. So we can deploy automatically pods, we can run the benchmarks, and the beauty of it, having the same set of benchmarks across VMs and containers, is that you can even compare the two solutions. What if a VNF is delivered as a virtual machine as opposed to a CNF delivered as a container, which has better performance? Which one can the infrastructure serve better? So long answer, but the short answer is yes, Kubernetes and containers is something that we do support.
Thank you, Vlad. And a reminder to the audience, please submit your questions. If we don't get to your question, we will answer it via email after this event. I think we have time for one, possibly two more. Next question. You mentioned some products for VNF testing, but they seem to be 4G focused. Are there any 5G VNF testing products in your portfolio?
Oh, yeah, Liz, I can take that one. We do have a new product called LoadCore that is specifically targeted at 5G. It emulates most of the 5G network elements and can benchmark a complete 5G core. It's a very sophisticated testing tool, fully containerized. It can be used both for lab testing or in a live network. And it can be used together with IXLoad VE or used independently. So
Great.
Thanks for the question.
So we're about up on time, so that's all the questions we'll take during this session. But if you did ask a question and we didn't get to it, we will answer it via email after this event. I'd like to take a moment to remind our audience to take that survey before you exit. We really take your feedback to heart and implement it in future events. There's also an opportunity there for you to request a demo if you want to see how this works in your environment. So thank you, Vlad and Bill, so much for taking us through all this content. And thank you so much to our audience. We really appreciate your participation.
Thanks a lot, everyone. It was very nice to have these attendees on the line, and looking forward to speak again to you.
Yes, thanks, everyone.
Thank you. Have a great day.